Hi everybody, it's Mrs. T. This is going to be a Regents Review video, and before we get started, you don't know who I am, I'm Mrs. Tominello. I'm a chemistry teacher at Calhoun High School in Merrick, New York, and I'm going to tell you a couple of things about what we should do to be prepared to watch this video. So the first thing that you should do is take out a reference table. You should also have a calculator, some paper, and something to write with so that you can work along with me. Those of you who are my students should make sure that they have an open Remind conversation so that you can respond to the Remind conversation with any questions that you have if this is one of the live streams. You can also go to my website and print out a copy of what we're going to go over. And I'd also like to thank Mr. Levy and Mr. Ludwig for sharing this file with me. What I'm going over came from Mr. Levy and Mr. Ludwig, so thank you very much to them. So we're going to start with average atomic mass. And the first thing that you should know is that the average atomic mass is what's found on the periodic table, and also that the average atomic mass is based on the abundance and masses of all of the naturally occurring isotopes of a particular element. If we want to calculate the average atomic mass, what we're going to do is we're going to take the atomic mass and multiply by its percent, and we're going to get a number. So if you follow along with me, 31.97 times 94.93% is 30.349121. 32.97 times 0.76% equals 0.250572. 33.97 times 4.29% is equal to 1.457313, and 35.97 times 0.02% is equal to 0.007194. If we want to get the average atomic mass, we are going to add all of these numbers together. 30.349121 plus 0.250572 plus 1.457313 plus 0.007194. When we add all of those numbers together, we get 32.0642. That number of atomic mass units is the average atomic mass of sulfur, because these are the isotopes, these are the masses, and the percentages of the naturally occurring isotopes. Percent times the mass, percent times the mass, percent times the mass, we add all of those up. And when we add them up, we get the weighted average, which is the average atomic mass. Something else to go over for nuclear reactions. If we want to know about mass being converted to energy, all nuclear reactions do this. All nuclear reactions are going to convert mass into energy, and so all nuclear reactions are going to give off a tremendous amount of energy compared to chemical reactions. But when they say the word fission, you are looking for something with a large mass before the arrow, neutrons on both sides, and two smaller isotopes after the arrow. So choice B is fission. Choice A is artificial transmutation, but doesn't have any specific name. Choice C is alpha decay, which is a form of natural transmutation. And choice D is an example of fusion. H plus H making HE is an example of fusion. So all of them were nuclear reactions, but only choice B was fission. For titrations, titrations are used to determine the unknown concentration of an acid or a base, and neutralization is the reaction that happens. So when you add a base to an acid, notice this is a base because it's a metal ending in OH. This is an acid because it's H in front. What's going to happen is that the H and the OH always make water, and then the other pieces, the NO3 and the Na, come together. We're going to look up oxidation numbers on table E for the polyatomic, on the periodic table for the metal or nonmetal. This is where you'd find those. We notice that they're the same charge or same number with equal and opposite signs, so they cancel out. So the formula for the salt is NaNO3. Remember, anytime you add a base and acid, you always get water plus a salt for your products. And remember that a salt is any ionic compound that's not an acid and not a base. When we talk about mole-to-mole conversions, you might see a balanced equation, and it might ask a question like, how many moles of water will be produced if 10 moles of oxygen completely react. So you'll know that it's a mole-to-mole question when you see how many moles of if this many moles of something else. So whenever they say moles of one substance compared to moles of another substance, you're talking about mole-to-mole conversions. What we should note, first of all, any place that there's not a coefficient, there should be an understood 1. That means that propane and oxygen react in a 1 to 5 mole ratio. And that carbon dioxide and oxygen have a 3 to 5 ratio. Water and oxygen have a 4 to 5 ratio. So you can use the coefficients as mole ratios. So if I react 10 moles of oxygen, that's twice 5. That means I'm going to get twice 4 for water produced. So 8 moles of water will be produced. Or you can go ahead and put the 10 on top of the oxygen and an X on top of the 4 and solve the proportion 10 over 5 equals X over 4. And when you cross multiply and solve for X, you will still get 8 moles. So the numbers from the word problem can go on top of the coefficients from the balanced equation to set up a proportion and solve. For Lechatellier's principle, remember this has to do with our equilibrium reactions. And remember that any reaction that's at equilibrium has equal rates and constant concentrations. So if a reaction is already at equilibrium, we have equal rates and constant concentrations. Lechatellier's principle states that if you put a stress on a system that's at equilibrium by changing concentration, changing temperature, or changing pressure, if there are gases involved, that will cause a shift in the equilibrium in a way that alleviates the stress. We used the memory tools add away and take towards. That means that if you add something, you shift to make more of what's on the other side. If you remove something, you shift towards that reactant or product to make more of what's on the same side. I always say that we should always put in our left and our right so that we can talk about shifting right or shifting left so we don't mix up our sides. And we also have the additional rule of increasing pressure shifts to the side with less gas. So if I increase the amount of nitrogen as my stress, that's going to shift right, which means that I make more ammonia and more energy. If I add more ammonia, that means that I shift to the left away from the ammonia, meaning that I will make more nitrogen, more hydrogen, and use up energy and use up ammonia. We can treat heat and energy as being affected by temperature. So if I increase the temperature, I will shift away from the energy term. Increasing the temperature will shift left. Decreasing the temperature will shift right. When I increase the pressure, I count up the moles of gas on each side. On this side, I have 1 plus 3, so I have 4 gas on the left. I only have 2 gas on the right, so increasing pressure will shift to the right because that's the side with less gas. For redox reactions, remember that redox reactions have to have a change in charges. The number of electrons lost has to equal the number of electrons gained. There must be a balance of charge. So here we have zinc 0 combining with lead plus 2, making zinc plus 2 and lead 0. So if I wanted to draw or write my half reactions for this, I would separate the reactants and products out by species. So zinc 0 turns into zinc plus 2, Pb plus 2 turns into Pb 0. Remember that when the charge goes up, 0 up to plus 2, we call this oxidation. Losing electrons is oxidation and the charge goes down. When the charge goes, losing electrons is oxidation and the charge goes up. When we're talking about the charge going down, we label that reduction. Gaining electrons is reduction and the charge goes down. When we have that happen, for oxidation, the number of electrons goes in the products, and 0 to plus 2 is a difference of 2. For reduction, however many electrons are gained goes in the reactants, and because, again, it was a plus 2 to 0, it's 2 moles of electrons here as well. For this reaction, we have Pb plus 2 electrons. Oops, that's not right. We have Pb plus 2 turning into Pb plus 4, which means that is a loss of 2 moles of electrons because the charge went up. For the Au plus 3, it's gaining 3 moles of electrons to turn into Au0. And this would be my reduction. I need to have the same number of electrons in each half reaction. So I'm going to multiply this entire half reaction by a 3, this entire half reaction by a 2, and what that does is it makes the number of moles of lead and lead ion change and the number of moles of gold and gold ion change so that we have the same number of electrons on each side, which means that in the balanced net ionic equation, we have coefficients of 3s for both of the lead ions and a 2 for each of the gold species. For a titration calculation, you might have a question that says something about what is the concentration of sulfuric acid if 12 milliliters of sulfuric acid is completely neutralized by 36 milliliters of 0.16 molar. These two numbers go together. These two numbers go together, which a question mark is an X. And remember that the formula is molarity of acid times volume of acid equals molarity of base times the volume of the base. However, because the acid has a subscript of 2, we're going to multiply the molarity of the acid by a 2. Since the OH does not have any subscripts, this side gets multiplied by 1 or gets multiplied by nothing. So that means that we would have 2x times 12 equals 0.16 times 36. And again, this is where your calculators will come out again. We wind up with 24x equals 5.76. Divide both sides by 24, and we get the molarity of the acid to be 0.24 molar. For BARF, remember, this is talking about bonds being broken and formed. When bonds are broken, energy is absorbed. Energy is released when bonds are formed. If two I atoms come together, this is forming a bond. Therefore, energy is released. This would be exothermic, whereas here, Br2 looks like this, whereas the Brs are separate from each other. So this is breaking a bond, which means that this is endothermic or absorbing energy. For parts of a voltaic cell, remember that we need to make sure that we look to see who's being oxidized and who's being reduced. And you might be given a reaction to start a question like this, such as Zn plus Cu plus 2 yields Zn plus 2 plus Cu. That would mean that the zinc going from 0 up to plus 2 is oxidized and is losing electrons. That would mean that the copper, whose charge is going down, would be reduced and gaining electrons. We always call the side of oxidation the anode. We always call the site of reduction the cathode. So that would mean that copper makes up the cathode and zinc makes up the anode. That would also mean that the flow of electrons is through the wire from the solid zinc metal to the solid copper metal. The purpose of the salt bridge is for the flow of ions, and the voltmeter will register the highest voltage when the when the switch is first closed, and the voltage will go down to 0 once the reaction has reached equilibrium. The cathode will get larger because this is where ions are turning into atoms. The anode will get smaller because this is where atoms are turning into ions. For the electrolytic cell, this is an example of electroplating. Actually, let's go backwards for a second. For the voltaic cell, it is spontaneous. For the voltaic cell, we are taking chemical energy and converting it to electrical. For the electrolytic cell, it is non-spontaneous, and we are taking electrical energy and converting it to chemical energy. The power source pushes the reaction. Because remember, this reaction would not happen on its own, so the power source pushes the chemical reaction to happen. So on this electrolytic cell, this again is electroplating. This is one type of electrolytic cell, and the object is always the cathode. The piece of metal is always the anode. The anode is still oxidation. The cathode is still reduction. So the metal gets oxidized at the site of the metal. The ions travel through the solution and they get reduced on the surface of the object. The electrons always go from anode to cathode. So they're going from the piece of metal through the power source, through the wire to the key. And again, the power source is pushing the electrons because of the fact that this is a non-spontaneous reaction. For formula writing, remember that we want to use the periodic table along with table E for ionic compounds. And for strontium phosphate, we're going to look up strontium on the periodic table, and we're going to look up phosphate on table E. Now, strontium is in group 2, so strontium has a +2 oxidation number, and phosphate is on table E, so we're going to start with parentheses before we crisscross. This 2 goes here, this 3 goes here, and that's why we get choice D here. For the metals that are in the transition metal section, groups 3 to 11, some of them have more than one choice of oxidation state. Those are the ones that get a middle name. Their middle name is the actual charge that they're using. So when you have these parentheses, you don't actually have to look up the charge on the table. They're giving it to you. We would then look up oxygen. Remember that IDE means use the negative charge. That means that the 2 and the 3 switch places, and we get B, Fe2O3. For copper 1 oxide, again, they're giving us the charge to use for the copper. IDE means use the negative choice for the oxygen. When we crisscross and drop the signs, remember 1s get canceled out, and we get Cu, oops, sorry about that, we get Cu2O as the final formula. For naming, FeS, again, we look on the periodic table and we see that iron has 2 choices for a charge. Anytime you have more than one positive oxidation number, you need to use parentheses for that element when it is first. So FeS, we have to figure out if sulfur, when it's a negative, is -2 and the charge is canceled out with no subscripts, that means that Fe is also a +2. Because this is just sulfur, that's why the sulfur ends in IDE. For NO3, this is covalent, so we use prefixes. We always drop the mono for the first element, and we use the prefix for the number that goes with the second element. Remember, it's mono, di, tri, tetra. Mono for 1, di for 2, tri for 3, and tetra for 4. When we balance equations, remember we're trying to get the same number of moles of atoms on each side. We start with a tally of how many of each atom are on each side. So I have 3 oxygens and 2 oxygens in the first one here, and this is the only thing that's out of balance. So I'm going to try to get each of these up to 6. I'm going to multiply this whole formula by 2 and this whole formula by 3, which gets them both up to 6. But this coefficient also doubles the amount of potassiums and chlorines that are on that side, which means that putting a 2 here doubles the potassiums and chlorines on that side. For something like this, where we have Mg, H, and Cl, again, I do my tally first. I see that it's my H's and my Cl's that are out of balance. By putting a 2 in front of the HCl here, I can get them all to be the same number. Coefficients multiply by the whole formula that comes after. You want to put in the coefficients until everybody has the same number of atoms on each side. For MSNAP, for molecular polarity and bond polarity, remember MSNAP is only about molecular polarity. Bond polarity has to do with two same is nonpolar bond, two different is a polar bond. So bond polarity and molecular polarity are two different things. Nonpolar covalent bond has to be two of the same. But if we want to talk about molecules, for molecules, symmetrical is nonpolar, asymmetrical is polar. My symmetrical nonpolar molecules of the bunch would be 3 of the choices that are there are all our symmetrical nonpolar molecules. The CCl4 is also a symmetrical nonpolar molecule. These are getting a little bunched up. Sorry about that. So those are all symmetrical nonpolar, and CO here is an asymmetrical polar molecule. Other good examples of asymmetrical polar molecules would be water. Remember that we have a negative side and a positive side here. Another famous asymmetrical polar molecule is ammonia. Remember that asymmetrical polar molecules have an unequal distribution of charge so that one side is positive and one side is negative, which is determined by the electronegativities. Higher electronegativity gets the negative side, lower electronegativity gets the positive side. Remember also that like dissolves like, so that things that are both polar molecules will dissolve in water. Things that are both nonpolar molecules will not dissolve in water, but will dissolve in each other. Okay, so for potential energy diagrams, remember since this one starts high and ends low, it's an exothermic potential energy diagram, which means that the delta H is a negative sign. The heat of reaction will be negative because of the fact that this is exothermic. 1, I'm going to make a 5 here. 1, 2, and 5 all measure potential energies because they all go to the axis. These are my reactants. This is my activated complex, and these are my products. So number 1 is the potential energy of the reactants. 2 is the potential energy of the activated complex, and 3 is the potential energy of the products, because that's the lines that they're going up to. However, if I make this a 6 here, 6 and 3 are both activation energies. They're activation energies because they go from a part of the graph up to, oops, I'm sorry, not 3. Let's make 3. 6 and 3 are actually the same line. Let's make 3 go all the way to here. 6 and 3 now are activation energies because they go from above the graph to the top. 6 is the activation energy for the forward, and 3 is the activation energy for the reverse. 4 is my delta H, and it's my delta hamburger. Remember, we have bun, and delta hamburger. Anything that goes in this central section here, it could go anywhere from left to right but it's going between the reactants and the products. That is my delta H. And remember that if I wanted to write this reaction, the energy term would be written in the products, and on table I, the delta H value would be negative. That's how we would know that the graph would be this shape, that it would be going downwards. That's how we would know that the energy was a product. If we wanted to add a catalyst, the only thing that would change in the graph is the height of the activated complex, so the delta H would not change because the reactants and products would not change. When we're talking about pure substances and mixtures, remember that if every molecule that you can pick up is the same, it's a substance. So this is a substance, and this is not a substance. This is not a substance. This is not a substance because each piece is different from each other. This one that is a substance has repeating units that have different elements present. So that one is a compound. This is a mixture of a compound and two elements, because this here represents two molecules of a compound. These are each molecules of different elements. This is a mixture of elements, right? This is one element. This is a different element. And this one here is a mixture of compounds, because this is a 1-to-1 ratio. This is a 2-to-1 ratio. Remember, for compounds, if the ratio changes or the proportion changes, you change which compound you have. For heating and cooling curves, this one is going uphill. So this is the endothermic curve. Any phase change on this curve would be endothermic. This is my solid, my liquid, and my gas. That means that this is melting and this is boiling. The boiling line is longer because it requires more energy to boil than to melt. Anytime the temperature is changing, so that would be here, here, and here, we have an increase in kinetic energy. Anytime the temperature is not changing, which is what happens at a phase change, we have an increase in potential energy. For when there is a temperature change, we would use the formula Q equals mc delta T. For these phase changes, for melting, we use Q equals MHF. For boiling, we use Q equals MHV. If we were talking about the cooling curve, which is the opposite, it would be exothermic, gas to liquid to solid. We would have condensation and freezing on the way down. Going downhill, remember, is always exothermic. For the bright line spectrum, what we should notice is that each particular element has its own characteristic bright line spectrum. This is produced when electrons from an excited state go back down to the ground state, releasing light. Oops. When this light is released, it can be broken up into different color patterns. Different elements will also have different color flame tests, but it's always when the electrons go from the excited state back down to the ground state that this light is released. We can use these bright line spectra to identify unknowns. In a mixture, all of the bands from a particular element would have to be found in the mixture for you to say that that element was present. So we can see that all of the barium lines are present. So barium is present in this mixture. These other two lines come from lithium. So this particular unknown mixture has lithium and barium. all of barium's lines are found, all of lithium's lines are found, and that's how we can tell that this is a mixture of lithium and barium. For intermolecular forces, when intermolecular forces increase, boiling point increases also. So stronger IMF means that you will have a higher boiling point. And as we increase the number of carbons for hydrocarbons or any other organic compounds within the same type, the boiling point increases. So more carbons, we have stronger intermolecular forces within organic compounds. When we talk about the combined gas law, when we talk about this, we're going to have the formula which is P1V1 over T1 equals P2V2 over T2. And if we look at a question and it says something about a gas and it says that we have a volume of gas and the temperature of gas and the pressure, and then we have a new temperature and pressure, this is how we know we're going to use this formula. Temperatures always have to be in kelvins, and STP can be found on table A. So we would put the first pressure which is 99.5 kilopascals, times the first volume, which is 45.6 milliliters, and put that over the first temperature, which is 283 Kelvin. Set that equal to the new pressure, which on table A, it's 101.3 kPa. We're looking for the new volume, and the new temperature is 273 Kelvin. We will then cross multiply and solve for X on our calculators. And I'll give you a second to do that on your calculator. Set everything equal and divide by what's in front of X. And when I did this, I got X equals 43.2 milliliters. You should also note that we have these different relationships for gas. We have two relationships that have temperature. We have temperature versus volume and temperature versus pressure. They are both direct relationships. And then we have a relationship that does not have temperature in it, which is volume versus pressure. This is the one that's inverse. So temperature goes up, volume goes up, temperature goes up, pressure goes up, volume goes down. When we talk about electron configuration and atomic or ionic radius, when we talk about calcium, calcium is a metal. And if we look on the periodic table, calcium has the electron configuration 2882. When calcium becomes a calcium ion, it loses these two electrons because metals lose electrons. Losing electrons is, sorry about that. Losing electrons is positive. So as it loses these two electrons, it becomes calcium plus 2. It only has now 3 shells, and its a new electron configuration is 288. So the calcium ion is smaller than the calcium atom because it has less electrons and less shells of electrons. You would have the opposite situation for a nonmetal. Nonmetals gain electrons and their ions are going to be larger. When we talk about calcium oxide, this is ionic. So we're going to draw the metal empty. Sorry about that. And the nonmetal full, meaning 8, stable octet. We take the charges off the periodic table. So calcium gets a plus 2, oxygen gets a minus 2. Because these charges are equal and opposite, we don't need any coefficients. But if we had magnesium, which is the metal which gets a plus 2 charge, And fluorine, which is a nonmetal, so it gets 8 dots and its negative charge, in order to balance the +2 and the -1, we would put a 2 in front of there. For ammonia, ammonia is nitrogen, which starts off with 5 valence electrons, which means that happy minus have means that it makes 3 bonds. Hydrogen starts off with 1 dot, which means hydrogen's happy is 2, minus its have means that it needs to make 1 bond. So each hydrogen needs to make 1 bond with the nitrogen. What they're going to do is hydrogen and nitrogen are going to bring these electrons together and share them. So nitrogen keeps these 2. It makes 1 bond with each hydrogen. Whereas chlorine has a happy of 8 minus 7, which means each chlorine needs to make 1 bond. So if each chlorine needs to make 1 bond, this electron and this electron are going to be shared. Remember, we can make a bond as 2 dots between, or those 2 dots can be turned into a line. So this is 2 electrons being shared in a nonpolar bond because it's 2 atoms of the same nonmetal. This is 2 electrons being shared in a polar bond. If we talk about MSNAP, this is the asymmetrical polar, this is the symmetrical nonpolar. If we talk about mole calculations, again, this is another mole-to-mole problem here. What is the total number of moles of HCl produced when 3 moles of H2 is completely consumed? You can either put a 3 on top of the H2 and an X up here, or you can say that they react in a 1-to-1 ratio. So if this one becomes a 3, this becomes a 3 also. If we want to know the total number of moles represented by 20 grams of CaCO3, we're always going to put grams given over the gram formula mass to get an answer, which means that we have to find the gram formula mass. So we're going to need to look on the periodic table. And on the periodic table, calcium has a mass of 40.08. In my class, we said we were always going to round to the 10th before we add. Carbon has a mass of 12.0. And oxygen, which we have to then multiply by 3, 16.0 times 3 gives us 48.0, which means that for this particular substance, when we add the masses together, we get a gram formula mass of 100.1 grams, and that's the mass that equals 1 mole. So we are going to do, to get the number of moles, what we are going to do is we're going to do 20 grams divided by 100.1 grams. And we are going to get 0.1998, so we're going to say that this is 0.20 moles, 0.2 moles. Now you could have put anything that was rounded properly from here, and I would say that you should have put the 0.20 or the 0.1998. Make it easy for yourself and round at an easy spot. But if they ask you for moles and they talk about liters and molarity, we're going to use the formula molarity equals moles divided by liters. And so we have a 2.0 molar solution, and we have 1.5 liters, which means my moles is my X. I'm going to cross multiply and solve for X. And X equals 3 moles. We talk about heat calculations. If we're talking about a change in temperature, we're going to look on table T and we're going to use the formula Q equals MC delta T. And Q always stands for heat, which we're asking for. The mass is my grams. The C value is on table B, and it's 4.18 joules per gram times Kelvin, which is the same size as the degrees Celsius degree, so we can sub that in there as the unit. And then for delta T, we have to subtract the temperatures. And when I subtract the temperatures, I get 10 degrees Celsius difference. I'm then going to multiply all of this out in my calculator, 50 times 4.18 times 10, and I get my answer of 2090, and the unit is joules. This was on table B, and the formula was on table T. If instead they're talking about the final temperature of the water, we're still using Q equals MC delta T, only I like to plug in delta T as my X. So 1,680 joules, 80.0 grams, 4.18 joules per gram, and then that can either go times degrees Celsius or kelvins, times X. And when I solve this whole thing and I do, and I get X by itself, I get that X is 5.02 degrees Celsius. But that's not the end of the story here. I need to reread the question, and it says that this water absorbs the heat. So that means that it goes from 10.0 degrees Celsius up by 5.02 degrees Celsius, and my final temperature is higher than the original 10 degrees Celsius. My final temperature is 15.02 degrees Celsius after this addition of heat. However, if we want to know about the initial temperature of the water, we need to find out how much heat was added. And so again, we're going to do Q equals MC delta T. We're going to plug in the 4,200 joules. We're going to plug in my 50.0 grams, my 4.18 joules per gram degrees Celsius, and I'm again going to solve for the number of degrees. My X comes out to 20 degrees Celsius, which means that if it went from somewhere plus 20 to get to 50, my initial temperature was 30 degrees Celsius. Before we end here, I realized there was no question about half-life in here, so I'm just going to give you a half-life question. So if you could please make sure you turn to table N. Okay, so for example, if we had a question like how many grams of a 100-gram sample of hydrogen-3 remain unchanged after 49.24 years, and they also maybe could ask what fraction of this remains unchanged, we would look on table N. And on table N, hydrogen-3 has a half-life of 12.31 years. That means in 49.24 years, 4 half-life periods go by. So you're always going to take the total time divided by the time for one half-life to find out how many half-life periods go by. Every 12.31 years, the sample of hydrogen-3 goes through one half-life. Every 12.31 years, or every one half-life, the amount remaining unchanged divides in half. So after the first half-life, there's 50 grams remaining. After the second half-life, there are 25 grams remaining. After the third half-life, there are 12.5 grams remaining. And after the fourth half-life, there are 6.25 grams of hydrogen-3 remaining unchanged. If we wanted to do this with with fraction, first half-life before we start, we have 1. After the first half-life, we have 1/2 remaining. After the second half-life, we have 1/4. After the third half-life, we have 1/8. And after the fourth half-life, we have 1/16. And if you wanted to, you could write the decay equation for hydrogen-3 by putting in the atomic number from the periodic table and the mass number up here. On the table N, it says that hydrogen-3 undergoes beta decay because it says B-. We're going to look on table O to find out the formula for that. We treat our arrow as an equal sign. 3 equals 0 plus 3. 1 equals -1 plus 2. And that means that in our natural transmutation of hydrogen-3, it emits a beta particle and turns into a nucleus of helium-3. This is a nuclear reaction. This is transmutation. And because it is a nuclear reaction, it gives off more energy, tremendously more energy, than a regular chemical reaction would. This was a video on Regents Review. Thank you again to Mr. Ludwig and Mr. Levy for the file that I went over in this video. If you have any other questions, please feel free to email me. And remember that Mrs. T's Chem Talk on YouTube will give you more of my videos. My classes, if you want to send me a message to ask questions about what was in this video so that I can go over it in our live streams that are coming up next week, certainly do so, and I can go back over any of these topics for you. Happy studying.